This week we're going to continue the kinetics experiment that we started last week. Hopefully you got all of your room temperature runs done last week. If you didn't, there'll be time to repeat one or two of those. So our task for this week is really to look more at the activation energy side of this kinetics problem. That means that we've got to look at temperature. So the main tasks for this week are setting up another cold run so that you've got 2 data points, or if your cold run last week didn't work very well, you'll get at least 1 data point at 0 degrees Celsius. And we want to set up a cool run. Room temperature was somewhere in the neighborhood of 20 degrees Celsius. Ice bath temperature is somewhere in the neighborhood of 0. Actually, if you maintain your ice bath, it's pretty rock solid at 0. So to give us a third temperature point, we want to go right in between. We want another temperature point somewhere right around 10. And we're going to do that with a cool bath. Cool bath isn't that hard to set up, but it's maybe not the most intuitive. So let's take a look at how we're going to set that cool bath up. Alright, so I have everything set up for my cool bath. So let's take a look at how we're going to make that and really maintain it. So cool bath is going to be in a large beaker. Not sure exactly what size they're going to be out, probably 800 milliliters, 1,000 milliliters, something like that, with water in them. So the thing we need to do is monitor the temperature of that. So you see I've got my temperature probe clamped into position. So let's go ahead and open up Logger Pro. Now, we're not really going to be using the data from Logger Pro for anything, but it makes for a pretty convenient way to just visually see what's going on. So Logger Pro is going to load up. It detects that there's a temperature probe attached, and right now it looks like my water is at about 22.4 degrees C. We're going to set this up to do a data collection, but again, it's not a data collection that we're going to use for anything in a calculation, really. It's going to be something that we're going to use to observe what's going on with our bath. So let's reset those limits, and I'll start it at 25. We'll probably lower it. We're going to want a bath that's around 10. So let me change that bottom limit to 5 to make it a little easier to see what's going on. I can turn on the stir and everything should be fine. Now, what else do we need to set up? This time is only for 150, 180 seconds. We want a really long time run. So let's go up in an experiment setup, go to data collection. Let's go ahead and tell it to do 1 sample per second, and let's do that for 20 minutes. You can do it for even longer than that if you really like. There, we're done. So now we're set up for a 20-minute data collection. Now let's just go ahead and click start. So we've got our data collection started. We want this to be around 10 degrees C. So grab some ice and start cooling. That first handful of ice, that first dose of ice is probably going to... Uh-oh, I need to set something up here. Let's stop this. Go back to data collection, and when I changed some of these settings, it changed to doing 1 sample per minute. Let's do 60 samples per minute so that it's sampling every second. Restart the data collection. And you see we've already cooled down quite a bit. So let me rescale this again. Let's go to 12 degrees and let's go to 8 degrees. So now I really zeroed in on exactly where I want to be. I'm still up at 12, so let's throw a little more ice in there. And there's my temperature. My temperature is going down. It's going down farther than I really want it to go down, but that's okay. It'll warm back up. All right, our bath is coming up to the temperature we want it to be, but this is actually a really good demonstration of why we can do this experiment the way we do, and one of the really fascinating properties of water. Water has a very, very high heat capacity. So once I got this water cold, once I got this water down to 8.3-ish degrees Celsius, it's taken 6-7 minutes just to increase the temperature 1 degree. So the heat is transferring from the room into this cold water, but because the heat capacity is so high, because it takes so much energy to change the temperature of this sample, we can have a fairly stable temperature as we run our experiment. So we're coming up a little bit closer, and since we're doing that, let me expand this graph even more. I'll run it from 11 down to 9. Now when we're doing our cold run, we want the temperature to be fairly constant. So how constant does it have to be? In a perfect world, it would be absolutely constant. But as long as you can keep the temperature within a couple tenths of whatever temperature you want to run your experiment, we should be fine. It doesn't have to be exactly 10. If you want to run it at 9.5 or at 10.5, that's fine. But try to keep it within a couple tenths. I'm going to let this warm up a little bit more before I do an actual experiment. But the other thing that we have to do is equilibrate the temperature. Just like with the cold bath, I've got a few set up over here. Just like with the cold bath, if I mix these warm samples together and then cool them down, I'm not going to get the answers I'm looking for, because I need these to be at bath temperature before they get mixed. Now, we could set up a whole bunch of clamps on this ring stand and hold them, but for this experiment it's pretty convenient, especially with the iodine. We can just kind of set it in there and it floats. That's not bad. With your other sample, there's more liquid in there, so it's a little bit denser. Sometimes those will float okay, sometimes they're a little low. You see it's swirling around a touch. If you want it to be a little bit more stable, there should be a test tube clamp in your drawer. You can always just throw the test tube clamp on that and that'll hold on to it. Those samples are just fine now. They should be in there for probably at least a couple minutes to equilibrate. And you can see in the data, when I added those warm tubes, it actually made the temperature warm up a little bit faster. So we're at about 9.5. I'm going to let this go up until, I'm going to try running this one right at 10. Okay, my temperature's made it up to 9.9, so I think I'm going to go ahead and mix them. They've been in there long enough that they should be equilibrated to temperature. So let me grab that and go ahead and mix. Now this one, you can keep track of any number of different ways. You can probably look at the clock on the wall. You could just make note of the time that's being collected there. You could keep a stopwatch going. I'm going to put the clamp back on that and get it back in there as soon as possible. So now my reaction has started. Just like with the cold run, we're going to observe this by eye. This is never going to go into a spectrometer. This is never going to do anything. It's just going to sit here and react in the cool bath. Just like with the cold run, it might be easier to see what's going on if you've got a sheet of white paper. That makes it a little bit easier to see the color. It might also help to have an actual blank. This is just water, just deionized water in a test tube. So you can compare the two tubes to see when it really does get colorless. Now you see that I've just crept up on my temperature to about 10.1. So how do we maintain a good temperature? Well, we can just throw ice, and here you see this is just two tiny little pieces of ice, and let's see how much of an effect that has on the temperature of the bath. Let's slow it down a little bit. Is it going to cool? If not, we can always grab a couple more little chips of ice. It really doesn't take many chips of ice to recool this down. So you see I still have some solid ice floating in there, and I might have gone too far because the temperature is really diving down. So it's at 9.9, thinks it's closer to 10. It looks like I was okay. So again, the only real purpose of this graph is to give us something to look at that's easy to quickly glance over at, and if the temperature has gotten too high, throw in a chip or two of ice and watch the experiment as it goes. So this is going to react until the color's all gone, and then we'll be able to start another run. So you can see my sample really just turned colorless. So my first run is done. Looking at the data on the screen, yeah, while it was reacting, I had to add ice a few times. And also looking at the data on the screen, I can say that I probably on average was closer to 9.9 degrees Celsius than 10.0. So for this run, I think I'm going to call it 9.9. I'll try to keep it at that same level for the rest of my experiments. And that's the only real new part of the experiment this week. You already know how to do the room temperatures, and you already have done a cold run. This is just the cool run that'll give us that third data point, so we can use the linear form of the Arrhenius equation to determine activation energy. So we should take a minute or two now to talk a little bit more about the calculations. Hopefully we're getting a little more comfortable with these calculations, but let's look at them just so that we can be sure. Okay, we've got data to work with. Now, how do we work that data up? Here's the reaction we're working with. Once we know what the reaction is, actually once we know what the reactants are, we can write out a rate law expression. So for this equation, the initial rate of the reaction is equal to the rate law constant K times the acetone concentration, initial acetone concentration raised to some power, let's call it A, times acid is a reactant, so H plus concentration raised to some power, let's call it B, and iodine concentration raised to some power, let's call it C. So there's our rate law expression. That's what we have to figure out all the values for. Right now, we can calculate concentrations and we can calculate rates from each of our runs, but we don't know the value of K and we don't know the values of A, B, and C. So let's start with concentrations. Those, hopefully you'll have done already. That would be great. If you don't, when we're talking about initial concentrations in a kinetics experiment, we have to be careful with our terminology. By initial, we mean the concentration after we mix everything together, but before we let any reaction take place. Now we know that physically that's not possible. As soon as things start to mix, they start to react. But for a kinetics experiment, we kind of make believe we can separate those two processes. So our initial concentrations are really just dilutions. So we can look at any of these. Let's just, for example, look at the iodine. So for your initial run, you were using 2 milliliters of iodine, and the concentration on that was, I don't know exactly what you're using, but they're all somewhere around 5 millimolar. So let's say 5.04 millimolar. There's C1, V1 equals, well, C2, that's what we're trying to find, the concentration after it gets diluted. And V2, if we assume that our 4 volumes are additive, V2 is 8.00 milliliters. So we can calculate that out. C2 is equal to 1.26 millimolar. So that's the initial concentration of iodine in the run if these are all of our numbers. You can go ahead and do that for all of your components, acetone, acid, iodine, for all of the reactions you did. Alright, so I figured out all my initial concentrations for the first run. So now we've got rate. Well, what about that rate? If that first run took somewhere in the neighborhood of 4 minutes, remember, rate is equal to, for this experiment, change in the concentration of iodine over negative change in the concentration of iodine over change in time. So for this experiment, we can do it in millimolar, we can do it in molar per minute. It doesn't really matter which unit we use as long as you keep track of your units. So let's do 1.26 millimolar over, and this first run took somewhere in the neighborhood of 4 minutes, so let's say 3.96 minutes. So our rate was 0.318 millimolar per minute. So there's our rate for the first run. In order to determine our rate law expression, we need data from 2 runs. So let's say it was 0.318 millimolar per minute for that first run. Let's get rid of all this. If we plug in the data for another room temperature run that we did, let's say maybe we doubled the concentration of acetone. If you double the concentration of acetone, you probably would get a reaction time somewhere around 2 minutes. So in that case, rate would be equal to, again, if we don't change the concentration of iodine, it's still just going to be 1.26 millimolar over, now say 2.01 minutes. So that rate is 0.627 millimolar per minute. So now we've got 2 runs. We can compare those 2 runs. By taking a ratio of their rate law expressions. So for the first run, 0.318 millimolar per minute equals K times concentration of acetone in that first run was 1.01 molar to the A. Acid, 0.243 molar to the B. And iodine, 1.26 times 10 to the minus 3rd molar to the C. To make things easier in this treatment, I just converted millimolar to molar. For the second run, we said the rate was 0.627 millimolar per minute. K, we doubled the concentration of acetone, the A, and the rest of the concentration stayed the same. So 0.243 molar, 1.26 times 10 to the minus 3rd molar to the C. So now that we've got our ratio set up, the reason we set these up is so that we can cancel K. 0.243 to the B, 0.243 to the B, those cancel, even though we don't know what B is. Those cancel, even though we don't know what C is. So we're left with what? We're left with something that looks like 1 over 2 is equal to 1 over 2 to the A. What must A equal? The reaction must be first order with respect to acetone. Now this is qualitative because I don't think this is exactly 1/2. We can figure those out mathematically. I have to use a logarithm, but you can figure those out mathematically. By doing that, you'll get some idea of the error in your measurement. So we can go ahead and figure out all the orders, A, B, and C. Once we know all the orders, we can plug back in and figure out a value of K. Now what about the activation energy part of the problem? To figure out activation energy, we need to use the Arrhenius equation. And for this experiment, we can use it a few different ways, because we've got 3 different temperature conditions, which means that we could use the comparative form a couple times, and we can also use the linear form. So comparative form of the Arrhenius equation, natural log of K1 over K2 is equal to EA over R times 1 over T2 minus 1 over T1. We can calculate a K for each temperature condition. We've got T, that's our temperature. R is a constant. We can calculate EA. So we can do room and cold for our 2 temperatures. We can do room and cool. And we can do cool and cold. So you should be able to calculate the activation energy 3 times using this comparative form of the Arrhenius equation. What about the linear form of the Arrhenius equation? Linear form is natural log of K is equal to negative EA over R times 1 over T plus natural log of frequency factor, A. How do we use this? Now, this is where people often run into trouble. You're used to plugging numbers into that comparative form and mathematically solving for the answer you're looking for. In the linear form, we're not just plugging numbers in and solving mathematically. The reason we want the linear form, the reason we use the linear form, is so that we can graphically determine what the activation energy is. And by doing that, we can get away from a little bit of the error. So the linear form, we've got 3 sets of temperature conditions. And for each of those different temperatures, we've got a value of K. So what can we do? Well, let's think about that. We've got K room and T room. We've got K cool and T cool. We've got K cold and T cold. So from that, we should be able to figure out natural log of K room, natural log of K cool, and natural log of K cold. We should also be able to figure out 1 over T room, 1 over T cool, and 1 over T cold. The advantage of doing this is now if we make ourselves a plot, and what's our plot going to look like? We've got linear form, so this is y equals m x plus b. So if we make a plot of what's y? Natural log of k, x is 1 over t. We just figured out our pairs of data. Natural log of k, 1 over t. So we're going to have 3 data points. Once we have those 3 data points, this is where the whole idea of a line helps us out. when I'm using the comparative form of the Arrhenius equation, I'm really relying on both of my data points to be really good, to be really correct. If they both have a little bit of error, if they both have a little bit of variation in them, that's not a good assumption. With the linear form, when I plot my 3 points, I can fit a line to those 3 points, and by fitting that line, you see these 3 points really aren't very linear. But if I fit a line to those 3 points, now the slight variations from experiment to experiment aren't as big of a problem because the line, the fit of the line, levels them out. From that fit, we should be able to get the slope, and the slope we said from our equation is equal to negative EA over R. So we should be able to calculate the activation energy for this process 4 times. 3 times by using the comparative form of the Arrhenius equation, once from the slope of the fit of the linear form of the Arrhenius equation, and we could probably just average those 4 values out to give us something that we believe as the activation energy for this process. And that's this week in lab. Probably not a lot of experimental work that has to be done, but there are quite a few calculations involved in working up this data. Good luck.